title. Okay, so I think we'll get started with today's class. So if we recollect, we were looking at the Bode plot yesterday, right? So we learned that the Bode plot has two subplots. The magnitude plot and the phase plot. Essentially, we have those two plots, plotted in a specific way, so that it helps us interpret things, right? So we learned that in the magnitude plot, we have the magnitude in terms of decimal measures, right? So where we take the logarithm to the base 10 and then multiply it by 20. Okay, so that's what we do in the magnitude plot. In the phase plot, we plot the phase in degrees, this is frequency, and in both the plots we have the frequency in logarithmic scale. And the advantage of having that, as we realized, is that we have the frequency, a larger range of frequency being plotted, and particularly, have also the low frequency range expanded, right? So that you and I can visualize what happens at the low frequency. So one advantage with the Bode plot is that you and I can, plot the Bode plot of individual factors and then add them to get the combined plot. So that's something we leveraged. So we had these individual building blocks, and we started learning what happens to the Bode diagram of each one of these blocks. We looked at the constant k, and then yesterday we had the integral term 1 by s, right? So in today's class, let's continue from there, and then let's look at what happens to the derivative term. Okay, yes. So if you look at derivative term s, if we substitute s equals j omega, the corresponding sinusoidal function is pretty straightforward, right? So we just get j omega. The magnitude of t of j omega is nothing but omega itself, right? Because magnitude is square root of real part squared plus imaginary part squared, right? So here real part is 0, imaginary part is omega. So we get the answer to be omega. So if we write in terms of decibel measure, this becomes 20 log omega decibels. And the phase is 90 degrees because we are dealing with when we are dealing with the j omega axis, we are essentially dealing with the imaginary axis, right? The phase is going to be 90 degrees. Okay, so that's how we get the phase to be 90, which is a constant. So if we do the same thing now, right, we did for 1 by s. So now we observe that the metrics, right, the magnitude is going to be something interesting. So once again, if we plot one decade above and below the corner of the frequency of 1, at 0.1, 20 log omega will be minus 20. At 1, it will be 0. At a frequency of 10 radians per second, 20 log to the base 10 is plus 20. So we can observe that this is exactly the mirror image of what we learned yesterday, right, for 1 by s. So with s, which is the 1 by s, there is some sort of reflection which is happening as far as the magnitude curve is concerned, right? So if we look at this particular plot, at 0.1 it's minus 20, at 0 at 1 it becomes 0 decibels, and at 10 at omega equals 10 it becomes 20, right? So consequently, there is a straight line which can be drawn through all these 3 points in the log magnitude plot, and the slope of the curve is 20 decibels per decade. how did we figure this out? If we go from 0.1 to 1, we go 1 decade up, we go up by 20 decibels. Another 1 decade up, from 1 to 10, we go another 20 decibels, right? So the slope is 20 decibels per decade. So what do you think is going to be the slope in decibels per octave for the factor S?
It will be 6, no, sir.
It will be plus 6, right?
Plus 6, right, sir.
For 1 by S, it was minus 6. For S, it will be plus 6. Okay. So you can check it. If you go, 1 to 2, right? If we do this calculation, let's say 1.5 and 2, 1 it will be 0, at 0.5 it will be minus 6, at 2 it will be plus 6. Okay, so once again, it's going to be sort of like a mirror image of what we done, right? For 1 by S. So the slope is 20 decibels per decade or 6 decibels per octave. Okay, so that is the result. Okay, so that's quite important. I hope it's clear. So we can observe that for the Bode plot of two factors which are reciprocals of each other, there's sort of like some symmetry which we are observing, right? So there's a reflection about a certain point. Okay, so this is a nice result, and that is expected, right? Because why? Log of 1 by A is minus log A. So at any particular value of A, log of A and log of 1 by A is going to have opposite sides, right? But equal in magnitude, right? So that's what we are observing, right? Okay. And the phase plot is a constant horizontal line at plus 90 degrees. Okay, so that's independent of the frequency, right? So this is how the Bode plot of the factor S will look like, right? So I hope the Bode plot of 1 by S and S are clear, right? Okay, yeah. So any questions about them?
Sir, we have plotted the Bode plot for 1 octave, right, sir? 0.1 to 1 and 10 in that way.
So what we have done is that we have plotted the Bode plot for 2 decades, 0.1 to 1 and 1 to 10. Okay. So we can keep on going. We can go
We
to
can extend
100.
it, right, sir? Okay.
So it's just that, like just for illustration, I have chosen this way. Okay. Anyway, the magnitude plot is going to continue as a straight line. Okay, in this decibel machine. All right.
Sir, one thing I want to ask is that basically by looking at the plot, Bode plot, like what I mean, it's a linear curve. Okay, sir?
No,
So
not necessarily. For this factor, it's a straight line. Okay. Yeah.
I should say straight line. I'm sorry. I used the wrong word, sir. I'm sorry for that.
No. I think, Roshan, what I meant was that I didn't want to differentiate it in linear and straight line. What I'm saying is that, like, next thing itself, we are going to learn that it can be a curve also. Okay.
Right, sir.
Need
So
not be straight lines all the time, right? So,
my question is that, sir, basically, as you have taught us in the previous class, that Bode plot is becoming very important. Whether when we are getting some data and plotting it, so by we can reverse engineer the what I mean to say is transfer function, right, sir?
yes.
So basically, looking at this, like suppose experienced person sees this graph, it's a linear one, I would say a straight line. So he can immediately come to know that it's a basically the transfer function of this probably this line will be something like which can be something related to, like he can guess the transfer function immediately in that way. Is that right, sir?
So yeah, that is the end application portion. So the as we discussed, first we will learn how to plot the Bode plot for each factor and combine them, right, to get a Bode plot for a transfer function. And in practice, when you and I get the data, we should be able to decompose the Bode plot from the experimental data to get the individual factors. Okay, so that's where we are headed towards. All right. Okay. So we will come back to this point. Okay, I will once again. This involves both theory and practice, right? As we keep on practicing, we will be able to figure things out. Okay. Yeah.
Sure, sir.
All right. Okay. So yes, please.
If you go up, how are we saying 6 dB per octave?
6 dB per octave, right? We did this calculation here, right?
The calculation is clear, sir. 0.5, 1, 2, and taking 20
Yes.
log. 0.5 to 1 and 1 to 2, how are we defining that as 1 octave?
That is the definition of 1 octave, right? What is 1 octave? If we go back, an octave, let's say you take a frequency omega, an octave is a range from that frequency to twice that frequency. Okay, that is the definition of the word octave. Okay, yeah.
Got it clear, sir. Yeah.
Similarly, 1 octave below is 0.5 times to that frequency. Okay. So, of course, one needs to remember this definition, because see, decade, it's very natural, right? A decade means immediately we can subconsciously associate it with the number 10. Octave means typically we associate with 8, right? It is intuitive, but then here it's twice. Okay, so that is a subtle thing. Okay?
Thank you.
Okay. All right. Okay. So now moving on, let's look at the next factor. Okay. So now we will see that things are going to become more and more interesting. Okay. So as we go forward, right? So next factor that you and I will consider is the factor 1 by Ts plus 1. Okay. So this has some interesting characteristics. So if we process this and we substitute S equals j omega, so we get the sinusoidal transfer function as 1 by Tj omega plus 1. That we can write as 1 divided by 1 plus j times t omega. Okay, so you and I multiply by the complex conjugate to extract the real part and the imaginary part. The complex conjugate is 1 minus j of j times t omega. So we extract the real part, which is 1 divided by 1 plus t squared omega squared, and the imaginary part is minus j times t omega divided by 1 plus t squared omega squared. So getting the magnitude is pretty straightforward. So by now, all of us know what to do, right? So the magnitude of this factor, right, which is this, is going to be the magnitude of the numerator divided by the magnitude of the denominator. What is the magnitude of 1? Magnitude of 1 is 1 itself. And what is the magnitude of 1 plus j times t omega? It's going to be real part square plus imaginary part square. Okay, so that's how we get the magnitude of this function to be 1 divided by t squared omega squared plus 1. Okay, so I hope it is clear how we got this expression. Okay, similarly, how do we evaluate the phase of 1 divided by 1 plus j t omega? It is going to be the phase of 1 plus the phase of 1 divided by 1 plus j2, right? The phase of 1 is 0 degrees. The phase of 1 reciprocal of a number is going to be negative of the original factor. So phase of 1 divided by 1 plus j t omega is going to be minus phase of 1 plus j t omega. And if you remember, the phase of a complex variable is tan inverse of the imaginary part divided by real part. Okay, the imaginary part is t omega, but the real part is 1. So that is why we end up with minus tan inverse omega, t omega. So I hope how we got these two expressions are clear. All right. So then we take the decibel measure, right, of the magnitude. We take 20 log to the base 10, 1 divided by square root of t squared omega squared plus 1. This we can write as minus 20 log to the base 10 square root of 1 plus t squared omega squared, right? How did we get this? Log of 1 by a is minus log a, right? That's what we have done. All right. So I hope it's clear how we got till this point. All right. So how we got the decibel measure of this particular block, right? Or factor 1 by tj omega plus 1. Now, in fact, Roshan asked whether, okay, we will have straight lines. Immediately you can see that here you are having a non-linear function of omega, right? It's no longer a straight line, right? If you look at the function. However, like we can plot what are called asymptotes. Okay, so what are asymptotes? As we already know, asymptotes indicate, like the, what to say, the limit of a function when we have a variable going to a limit, right? So in root locus, you and I plotted asymptotes to figure out what happens when, like S tends to infinity and so on, or K tends to infinity and so on, right? So similar idea we are going to use here. But the only thing is that now we are going to look at asymptotes at very low frequencies and very high frequencies. So at low frequencies, we define low frequencies to be omega. This double less than means very, very less than, okay? 1 by capital T. Let's say if capital T is 1, 1 by capital T is 1. We take omega to be 0.01 or 0.001 or 0.0001. Okay, like, so you get the idea, right? At very, very low frequencies, what it is. So when omega is very less than 1 by T, if you cross multiply, you can see that T omega is going to be very much less than 1. Then what can we say about 1 plus T squared omega squared? Let's say T omega is 0.01. What will be T squared omega squared?
0.001.
So if T omega is 10 power minus 2, T squared omega squared will become 10 power minus 4. So if I add 1 to 10 power minus 4, what can I say about the result? It's pretty much close to 1, right? Is it not? Correct? So what we do is that we simplify. This is approximately equal to, this simple means. So at low frequency, the magnitude minus 20 log to the base 10 square root of 1 squared plus T squared omega squared can be approximated as minus 20 log 1. And that becomes 0 decibels. Why? Because log of 1 is 0. Okay, so I hope it's clear how we got 0 decibels as the low frequency asymptote. Okay, so I hope now it's clear why we call 0 decibels as a low frequency asymptote of this factor 1 by Ts plus 1. So what this means is that the magnitude of d of j omega tends to 0 decibels as omega tends to 0. Okay, so that is the meaning of this particular next step. I hope it's clear. What is the low frequency asymptote? So let me repeat again. We are dealing with the factor 1 by Ts plus 1. We observe that when we derive the magnitude of this factor in decibels, it is minus 20 log to the base 10 square root of 1 plus T squared omega square decibels. That is a nonlinear function of omega, but we are trying to approximate at low frequency and high frequency. At very low frequencies, the magnitude is going to go to 0 decibels. Okay, fine. Now let's see what happens at very high frequencies. So let's say 1 by T is 1, right? Once again, for example, okay. Then let's say I take omega to be 100 or 1000. So you can immediately see that we are talking about high frequencies. So consequently, T omega is much, much greater than 1. Let's say T omega is 10 power 2. What can we say about T squared omega squared?
It will be very high. 4.
10 power 4, right? Now, if we put 1 plus 10 power 4, this is approximately going to be equal to 10 power 4, right? So 10 power 4 is 10,000. So see, 10,000 plus 1 is 10,001. I can call 10,001 to be almost 10,000, right? Is it not? So we are doing an order of magnitude analysis. So when I do this, right? So immediately you can observe that, like we can do this approximation. The magnitude, which is 20 log square root of 1 plus T squared omega squared. You and I can replace 1 plus T squared omega squared with just T squared omega squared. I hope this step is clear, right? And when we take the square root of T squared omega squared, we just get T omega. Okay, so this is what we get as the high frequency asymptote. Okay, so the high frequency asymptote is minus 20 log T omega decibels. Now, this high frequency asymptote is a straight line. Okay, so I'm coming back once again in relation to the question asked by Roshan, right? In reality, the magnitude plot of this factor 1 by Ts plus 1 is a nonlinear function, okay, even when we plot in decibel. But when we approximate it using these asymptotes, this high frequency asymptote is a straight line And if we calculate, let's calculate minus 20 log t omega in decibels, starting from the frequency 1 by capital T. Okay. So at 1 by capital T, what do you think will be this value? When omega is 1 by capital T, what is T times omega?
It will be 0, sir.
Yeah, T times omega will become 1. And then I take
Yeah.
log of T, it will become 0, right? Correct. You will get 0 decibels. I hope it's clear. Now, if I go 1 decade above 1 by capital T, which is 10 by T, what do you think will happen? We will get minus 20 log of 10 times T, sorry, 1. Let me write it in a specific way. T times 10 by T. Okay, so T and T gets cancelled. So what do we get? We get minus 20.
Minus 20, yeah.
So you see that we get minus 20, right? So you can observe that this is a straight line, this high frequency asymptote with a slope of minus 20 decibels per decade. Okay. So if we want to draw the asymptotic value of the magnitude plot of the factor 1 by Ts plus 1, we draw the low frequency asymptote, which is the 0 decibel line, okay, and the high frequency asymptote, which essentially intersects the low frequency asymptote at 1 by capital T. Why do you think it intersects the low frequency asymptote at 1 by capital T? What is the low frequency asymptote? It is
0.
0 decibel. When does the high frequency asymptote become 0? At omega equals 1 by capital T. Okay. So I hope it's clear how the low frequency asymptote and the high frequency asymptote intersect at 1 by capital T. Okay. For this reason, 1 by capital T is what is called as a corner frequency or the break frequency. Okay. In the context of this analysis, it is the frequency at which the low frequency asymptote and the high frequency asymptote will intersect. Okay. So why were these important? For this, we need to go nearly a century before. See, today you and I have access to all these digital computers and so on, right? So you and I can readily plot the Bode plot using one single command. If you use the command Bode in MATLAB, in a matter of couple of seconds, we will get the Bode plot plotted. Okay, no doubt about it. But imagine, like before 1950s or 1960s, right? Before the digital circuit was invented, people used to plot by hand, right? And plotting the complex functions by hand was very challenging for the first cut analysis. So they used to have asymptotes so that they can plot these straight lines using a paper, pencil, and scale. And then they could do the analysis and then come to the actual plot as and when needed. Okay. So that is the practical engineering motivation of studying these asymptotes. I hope it's clear. All right. But then one may ask the question, okay, I learn this. The reason, once again, is that it always helps us to do it by hand so that when we are studying the inverse problem, that is, what is the inverse problem? From the experimental data, you and I want to figure out the transfer function. Visualizing these asymptotes is very, very useful. Okay. That is why you and I are studying it. Okay. So I hope this train of thought is clear to all of us. All right. Okay. So the point of intersection of the two asymptotes is 1 by capital T, and that is the corner frequency or the break frequency. So if, let's say, somebody asks us to draw the Bode plot of 1 by Ts plus 1 by hand, it's okay to draw the two asymptotes, okay, the high frequency asymptote and the low frequency asymptote. Okay, the low frequency asymptote is the 0 decibel line. The high frequency asymptote is a straight line with a slope of minus 20 decibels per decade. What do you think is going to be the slope in decibels per octave?
-6.
By now, right? Minus 20 decibels per decade corresponds to minus 6 decibels per octave, right? So you can convince yourself, right? How do we convince ourselves? If I put, if I evaluate a 2 by T, what will be minus log t times 2 by t? It will be minus 6. So you will see that you will get minus 6. Okay, so the slope will be minus 6 decibels per octave. Okay, so this is the shape of the factor 1 by ts plus 1. Now, from a practical perspective, you can immediately see that it looks like a low pass filter. Why do you think it looks like a low pass filter?
Because it is cutting the frequency beyond a certain value of like omega.
So you can see that till this corner frequency 1 by t, it is allowing the signals to pass, right? It is not doing much to the signals, input signals. But below the corner frequency, you can see that it's attenuating the high frequency components. Okay, that is the characteristic of a low pass filter. All right. So now I hope it becomes clear when I think I told you that I will revisit this point when we discuss frequency response, right? Do you recall one question I asked? I asked you to go and find out how the derivative controller is programmed in practice. Did you go and check it out? The derivative controller was KDS, right? How do you think this is programmed? Even as a MATLAB block. So what was one limitation with the derivative controller? Do you recall?
Steady state error, sir.
Steady state error. Okay. Derivative controller block. See, we studied about PID, right? Proportional integral derivative, right? If you refer your notes, what was one limitation?
Basically, it will amplify the low frequency attenuations.
It will amplify? No. Yeah, you
Yes.
are correct. Continue.
Yes, sir. It will amplify the low frequency signals.
Okay.
Noise also, sir. Noise actually.
Yeah. Yeah, let me just add on to that. It will amplify. You are right. It will amplify the noise. Noise is low magnitude, high frequency. Okay, so it will amplify the low magnitude, high frequency signal. So if I want to avoid that, what should I do? I should filter the high frequency components. And what is a simple way to do that? I integrate multiply the derivative controller block with this 1 by ts plus 1. This is the simplest block we can use to get this low pass filter characteristics. So you will see that even in Simulink and MATLAB, they will suggest using this for the derivative controller block, okay, to essentially ensure that we essentially filter off, right? Like the high frequency. All right. I hope it's clear. Okay, so why it is called, why it takes the shape or how 1 by ts plus 1 corresponds to a low pass filter, and how like we integrate it with the derivative block, and then like we are able to filter out the high frequency components and ensure that one advantage or limitation of the derivative controller is taken. I hope this clarifies that part. Okay. Yeah. All right. Okay. Now we come back to our body block. Okay. So we went to derivative control realization. So what you and I have done, if I can redraw this figure, because I have drawn on top of whatever I have already drawn, right? So we wanted to plot this block in decibels. What you and I have drawn is, we have drawn a low frequency asymptote at 0 decibels till 1 by t, and a high frequency asymptote having a slope of minus 20 decibels per decade. Okay, so that's what we have drawn. So we have drawn two straight lines, okay, for the factor 1 by ts plus 1. Now the question is, what is the actual magnitude plot of 1 by ts plus 1? Okay, for that we construct this table. Okay, so I will explain this table, but you please do this also as an independent exercise. Okay, you try it out on your own, and then we essentially are able to look at the difference between the actual magnitude and the asymptotic value. Okay, so what we do is that we do the following. We start with the corner frequency 1 by capital T. We go 1 decade below and 1 octave below the corner frequency, and then 1 octave above and 1 decade above the corner frequency. What is 1 decade below the corner frequency of 1 by T?
Half of the frequency, sir.
0.1 by T.
1 decade below, right? It should be 0.1 by T, right?
Yes.
1 octave below 1 by T is half of it, right?
Half. Yes.
0.5 by T. 1 octave above is twice of that. So we'll get 2 by T, right? 1 decade above 1 by T will be 10 by T. Okay, so that's what we. All right. So what we are plotting is that in this column with the pink elements, we are plotting the actual magnitude. Okay, so this is the actual value. What was the actual magnitude? It was minus 20 log to the log of square root of 1 plus t squared omega squared. Okay, in terms of decibel measure. Okay, that is the actual magnitude of the block. What is the asymptotic value? What were the asymptotes? It's 0 decibels below 1 by t, right? And minus 20 log d omega above 1 by t. Okay. At 1 by t, it is 0, right? So I think that we know that, right? So now let us start with 0.1 by t. How did we get the value as minus 0.04? I will do the calculation once to explain. So this will be minus 20 log square root of t squared omega squared. So what do we need to do? We need to substitute for omega 0.1 by t. So what will be 0.1 by t whole square? It will be 0.01 divided by t squared. I hope everyone is clear, right? So then this t squared and t squared will cancel off. We will get minus 20 log to the base square root of 1.01. Okay, that is the actual value. And if we evaluate this number in your calculator, you will get the number as minus 0.04 decibels. Okay, I hope it's clear how we got minus 0.04 decibels as the actual magnitude. Okay, so I hope that's clear, right? Any questions? Okay, so what is the asymptotic value? The asymptotic value is 0. So what is the difference between actual and asymptote? It's minus 0.04 decibels. Okay, the actual is minus 0.04. The asymptotic value is 0. So the difference is minus 0.04 decibels. Now we do the same thing for 0.5 by t. What do we do for 0.5 by t? Now I substitute. Then omega is 0.5 by t. So we will get 0.25 by t squared. So t squared will get cancelled. We'll get minus 20 log to the base 10 square root of 1.25. So if we calculate this, we will get minus 0.97 decibels. Okay, so this will be the actual magnitude, right? And 1 octave below the corner frequency. What is the asymptotic value? It is a low frequency asymptote, right? At 0 decibels, right? Below the corner frequency. The low frequency asymptote is 0 decibels. So now you can see that the difference is minus 0.97. So you can observe that as we keep on approaching the corner frequency, right? Our error between the actual and the asymptote, okay, is keeping on increasing. Okay, so this is the observation we can conclude, right, from this term. But let's proceed. Okay, now we come to 1 by capital. What do we do? I hope by now you know what needs to be done. So why don't you help me here? So I substitute omega equals 1 by t. What will I get?
Minus 20 log 5, sir.
I'm sorry, what is that? Minus 20 log 5?
minus 20 log under root 5.
Root 2, sir.
So Roshan, I'm talking about 1 by t, right? So
Oh,
this will become
sorry.
t squared times 1 by t squared, right? So what you're talking about is 2 by t, correct, right? But let's go 1 by t. So we'll get minus 20 log to the base square root of 2. Okay, that will be minus 3.01 decibels. So the difference becomes minus 3.0. Okay, so I hope it is clear, right? So slowly you can see that the difference has increased. Under the corner frequency, actually the difference between the actual and the asymptote is the maximum. Okay, then we go to 2 by t. As Roshan said, now it will become minus 20 log of square root of 5, which will be minus 6.99. However, it's important to note that the high frequency asymptote is minus 20 log t omega. So here, how did I get minus 20 log 2? I need to substitute omega equals 2 by t. So I get minus 20 log 2, which is minus 6.0. So the difference is minus 6.99 minus of minus 6.02, which is once again 0.9, minus 0.9. So you can see a symmetry around the corner frequency, right? Whether it's 1 octave below or above the corner frequency, the difference between the actual and the asymptotic value of the magnitude is minus 0.97 decibels, right? Then we go 1 decade above. 1 decade above means the actual value will be minus 20 log of square root of 101, which will be minus 20.04. Asymptotic value will be minus 20 log of t times omega is now 10 by t, which will be log 10. Okay, this will be minus 12. So the difference is once again minus 0.04. So you can see that the difference is symmetric around the corner frequency. Okay, so there are two observations. One is as we approach the corner frequency from either end, whether it's from low frequency or high frequency, what happens is that the error between the actual and the what to say asymptotic value keep increasing, right? So that is one observation, right? Then the second observation is the difference between the actual and asymptotic value is symmetric about the corner frequency 1 by capital. So if you and I plot this, you will see that the error plot will come something like this. So the conclusion that is important for us is that if we end up using the asymptotes instead of the actual plot, we will essentially get a maximum error of minus 3 decibels in our magnitude plot. Okay, so that is the main conclusion from this particular analysis. Okay, I hope it is clear, right? Now, as the last step, we need to plot the phase plot. So if you recollect, the phase plot of this factor is minus tan inverse t omega. We have already derived it, right? If you remember, we calculated it some time back. So now, if we plot a similar table at the corner frequency of 1 by t, if we substitute omega equals 1 by capital T, we will get the phase to be minus tan inverse of t times 1 by t. So t will cancel off. So that will be minus tan inverse of 1. And what is tan inverse of 1?
45, sir.
So the phase will become minus 45 degrees. As omega tends to 0, the phase will go to 0. As omega tends to infinity, the phase will tend to minus infinity. So you will see that the phase curve is a nonlinear curve with an inflection point at 1 by t. Okay, this is the shape of the tan inverse curve, right? Okay, so consequently, that's something which we need to, look at. Okay, so essentially, we have, what to say, phase, right? To be following a nonlinear trajectory with respect to omega, okay, in the shape of a tan inverse, right? So this is the phase. So what we have learned today is the Bode plot of 1 by Ts plus 1. Okay, so where you and I have learned how to construct the magnitude plot and the phase plot of this factor. We constructed the low frequency and the high frequency asymptote of this factor. The low frequency asymptote was the 0 decibel line. The high frequency asymptote was minus 20 log t omega, which is a straight line with a slope of minus 20 decibels per decade or minus 6 decibels per octave. And then we did an error analysis where we calculated the difference between the actual and the asymptotic value. We observed that the difference between the actual and the asymptotic value was the maximum at the corner frequency. The value was minus 3 decibels, and it was symmetric around the corner frequency, right? And it kept on decreasing to 0 as we moved away and away from the corner frequency. So, and then we also plotted the phase plot, right, to figure out how the phase plot looks like. Okay. So, you can try out the Bode plot of TS plus 1. We will start our discussions from here tomorrow, but then you will observe that once again we will have a low frequency asymptote and a high frequency asymptote. It is going to be exactly the mirror image of what we learned today. 1 by capital T will still be the corner frequency, but now the larger frequency or the higher frequency will be amplified. Okay, the magnitude at higher frequencies will keep on increasing, and the phase will go from 0 to 3. So you see that there is a symmetry, right? Once again, when we have the reciprocal of the factor that you and I are considering. Okay, so we look at TS plus 1 tomorrow, and then we will move on to second order factors. All right. Okay. So any questions on what we have learned today?
Sir, not questions, but just one common thing that maybe this class we weren't much interactive, but maybe next class we will be much interactive. Sir. Just wanted to say that.
Okay.
Because we were also trying to assimilate whatever is getting taught for the first time. So for those reasons, we couldn't ask much questions.
Yeah. I understood, Prem, because today I had to explain the notion of asymptotes and how these things are calculated, right? Which we are learning for the first time. Okay, so that is why maybe today's class might have been more like a monologue where I only asked you some values to fill in, right? So that's it, right? So.
Exactly the same thing, sir. I didn't want you to feel that it was a monologue. That's why I wanted to interject and say this point. Thank you, anyways.
Yeah, sure. Point well taken.
Sir,
Yes, please.
so these asymptotes, let us say very low frequency and very high frequency asymptotes, will it always intersect at 1 by T?
So in this particular case, may I know who this is?
Sir, Vikas.
Vikas. Okay. So because in this particular example, it is at 1 by capital T. Okay, for this factor. All right. So when we go to the second order factor, you will see that it will intersect at omega n. Okay, which will be the natural frequency. Okay. So it really depends on the factor because. Okay. So for the factor 1 by Ts plus 1, it is essentially intersecting 1 by capital. Okay, that's all there is. Okay.
Okay, sir.
And at the point of intersection of the low frequency asymptote and the high frequency asymptote is what is called as a corner frequency. So that's right.
And sir, one more question I want to ask, sir. Basically, we have taken the the omega value is like 1 octave and a decade lower and upper, like 0.1 to 10. Suppose if I want to extend it to 0.01, sir, like will there be any dip in the curve going?
Yeah, you will see that the difference will keep on decreasing. Why don't you try it out, Roshan?
Okay, so, it will be exactly equal to what I meant to say asymptote, right, sir?
So if you calculate the error for 0.01 by T and 100 by T, okay, the errors will be the same. Okay, yeah.
Oh, thank you, sir. Thank you so much.
Okay. Arunachalam, is everyone present today? No, sir.
Sir, everyone present, sir. All are.
Fine. Okay. So, yeah. So, any other questions? I think we have still a couple of more.
Sir, one question. Basically, sir, now that we know that at corner frequency only we have the maximum error, can we not assume a value of corner frequency instead of having assumed that asymptote there, can we not simply calculate the value at 1 by t itself and
Yeah.
minimize the error?
Of course, yeah, yes, because see, as I told, I gave a brief historical perspective of why we plot asymptotes, right? In addition to the practical significance, which you and I will learn later. The historical thing is that, see, imagine I are now plotting only for one factor, but in a general transfer function is going to have multiple factors, right? Point number one. Then imagine that we lived in 1940s when we didn't have all these calculators. Okay, you and I needed to plot with our hands and calculate with our brains, right? So, for a first cut approximation, people used to plot with scale and pencil with the asymptotes. And then you know that at the corner frequency, you need to apply a correction of 3 decibels or minus 3 decibels. So you mark that on the graph sheet and then plot. Okay, so but this theory provides you the basis for it. I hope it's clear what was the historical connotation of these steps. Okay.
Yes, sir.
Today, as I told, you type the command Bode in MATLAB prompt. You know, in 2-3 seconds, you will get the Bode plot. You know, like actually calculated. You know, without you won't even see. So try it out. You know, like so. In fact, if you try to plot the Bode plot of 1 by ts plus 1 in MATLAB, you will see a non-linear curve. Okay, so what I have labeled as actual. Okay, you won't get this asymptote at all. Okay, so now we have this particular facility, right? But then previously, when these computing facilities were not available, right? People used to use these asymptotes to get the first cut approximation. Okay, so that is the context. All right.
Sir, one thing I want to ask. Sorry, probably a last question from my side, sir. I'm not sure whether I'm asking the right question or not. Suppose that this like function which we have like ds is equal to ts plus 1 or maybe 1 divided by ts plus 1 is there. But suppose if the ds function is the polynomial function, which is like suppose tertiary function, like 1 t cube s cube plus t square plus some constant. In that particular function, or maybe we can extend it to n polynomial, order polynomial,
yes.
whether the number of asymptote will increase, sir, in that case?
So you
Just
plot for
to...
each factor, Roshan. That's exactly where we are getting to. Okay, so where did I write it? Okay, so in general, P of S is like this, right? K times S plus Z1 all the way till S plus Z1 divided by S plus P1 all the way till S plus P. That is the general structure, is it not, Roshan? Now, the point is, you and I, even if you take your example where you assume the third order polynomial, you can always factorize it to first order and second order polynomials. That is why we are considering these blocks. Okay, we will observe that any transfer function that you give me, I can factorize into a combination, a product of these factors. Okay, that is why we are learning the Bode plot of the individual factor. And once we learn the Bode plot of the individual factors, the Bode plot of the composite factor transfer function, it will be obtained by just adding the individual plots. Why? Because of the property of the logarithm. All right, that we have been learning.
Thank you, sir. You had already answered this question. I'm sorry.
Yeah, no problem.
Probably
right?
I could comprehend now completely.
Yeah. We are slowly getting there. So, but then the main challenge is that in real life, you will get a composite Bode plot. How do you then figure out by observing, what are these factors which come in? That's where you and I are getting to. Okay. So that is why I am teaching these techniques to you, because we have used it in practice in automotive control applications, right? So that is the reason why I am spending quite a bit of time, because I feel that for experimental determination of transfer function and designing automotive controllers, at least at the first level, these techniques are quite useful. Okay, so that is the reason why I have included them in this course.
Thank you so much, sir.
Sir, one basic query from our side. Sir, we are essentially saying systems are Bibo stable, right? In that condition, I'm just trying to articulate my question. Maybe I'm wrong also, but if Bibo stability we are talking, then this asymptote existing condition, which means that it is tending to infinity, should not come, right? It is not within the bounded input, bounded output,
so
right?
the asymptote, what to say, essentially, like being, like going to infinity does not mean that the system is not Bibo stable. Okay? The point of Bibo stability is that, like, if you and I give a bounded input, the output should be bounded for all time, right? See, asymptotic value is only a limiting value. Okay, so the point that you and I are making is that, like, if omega tends to infinity, what is sine infinity t? That also doesn't make sense, right? Is it not? Right?
Yeah,
So
okay.
we only look at limiting. That is the notion of limiting values, right? A limiting value. See, it is a useful concept in mathematics. In engineering, you and I are not going to encounter it, but then, like, we study it. Okay, that's it. Like, let's look at it then. All right.
Okay, sir, noted. Yeah.
Okay, so I think we will continue from here tomorrow. We meet at 5, and then, like, we will continue with the other factors. Okay.
Thank you so much, sir.
Yes, sir. Thank you, sir.